Next section is 3.6. And we're going to continue talking about polynomials. So the first thing that we're going to talk about is the rational root theorem. The rational root theorem says that if there is a rational zero, if the zero exists, it is a factor of the constant term over a factor of the leading coefficient. That's what the rational root theorem says. And the reason why that is because if we think about the relationship between factors and constants, let's just say that we had a quadratic that when I factored it, it was 2x plus 7 and 3x minus 4. Are you okay?
Okay.
You're all done?
Yeah.
Here. So if I were to multiply this back together, I would get 6x squared, 21 minus 8, so 13x minus 28, right? My zeros, though, would be negative 7 over 2 and positive 4 over 3. You see how the 7 and the 4 made the 28? And those are my numerator numbers. The 2x and the 2 and the 3 made the 6, and those are my numbers in my denominator. So it's because of the relationship between factors, polynomials, and zeros that this rational root theorem exists. Okay, because if you take the zeros, the numerators, excuse me, of all of your zeros, if you take all of your numerators and multiply them together, you're going to get your constant term. And if you take the denominators of all of your zeros, you're going to get your leading coefficient, because this becomes the numerator and this becomes the denominator. This times this is the constant term. This times this is the leading coefficient. So it's that relationship that gives us this rational root theorem. So if there is a rational zero, it is a factor of the constant term divided by a factor of the leading coefficient. Okay. So in order to determine which ones of these are possible, we're going to factor 35. That's my constant term. 1, 5, 7, 35. And we're going to factor 33. That's my leading coefficient. 1, 3, 11, 33. And so then my possible zeros would be all of these over all of these. So the numerator has to be one of these numbers and the denominator has to be one of these numbers. So 5, 5, 7, 1, 7, all my numerators are factors of my constant term. But is 7 a factor of 33? No. So since 7 is not a factor of 33, it can't be one of my denominators. So that's the one that is not possible. So my numerator should always be factors of my constant term, and my denominator is factors of my leading coefficient. Okay. Now, when you're asked to write a polynomial in factored form, my advice is to always graph first. And we're going to get as many zeros from the graph as humanly possible. Aria, what's wrong? You need squeezies? You say please? There you go. 20x to the 5th plus 138x to the 4th plus 362x to the 3rd plus 444x to the 2nd, oops, plus 248x 20x plus 48. All right, let's just double check it. I am notorious for filling in something wrong on these. 20x to the 5th, 138x to the 4th, 362x to the 3rd, 444x squared, 248x, 48. Okay, looks okay to me. So always graph first. Now this is a 5th degree polynomial, so I'm expecting to be able to find 5 zeros. All right, that's weird. Let's take a look at the table and see if there are any zeros that we can find from the table. You all done? You want this one?
I'm done.
All done.
And then
You got one more? Did my table come up yet? Nope. There we go. So we call them zeros because it's where the y value is 0. So from the table, I can tell that I have zeros at -2 and -1. Definitely. So those are my definites. Now, if I zoom into the graph, I want to look at what's going on around here. So let's change my window. And I want to go from -5, let's say, to 2. And then let's say -5 to 5. And again, this is just a guess because based on what we saw, I was like saying, okay, I want to be in about this area. Okay, so you see how right here it bounces at -2? So that means -2 repeats. That means that the -2 is actually there twice. Because that means that that would have been an x plus 2 to the 2nd power. Remember we talked about that last time. How if it bounces at a 0, then that means that that factor had multiplicity 2. Okay? At 1, it goes straight through, so that's multiplicity 1. Now I see I have another 0 in between -1 and -2. And I have another 0 in between 0 and -1. Okay? So that's important because I need all 5. I have 3. I need to figure out what those last 2 are. So my first step is always to divide out the zeros that I have using synthetic division. So I know I have a 0 at -2. We multiply, we add, maybe 98. We multiply, we add, we multiply, we add, we multiply, we add, we multiply, we add. I'm going to divide out another -2. That's -40. And then we add. So that's going to be 58. And then we multiply. And then we add. And then we multiply. And then we add. And then we multiply. And then we add. Now I'm also going to take out the -1. Multiply, add, multiply, add, multiply. So if this was x to the 5th, every time we do synthetic division, we take the degree down by 1. So if this was x to the 5th, this is x to the 4th, this is x to the 3rd, this is x squared. So what I'm left with is 20x squared plus 38x plus 12. Well, first of all, there's a GCF of 2 here. There was a GCF of 2 all the way up at the top that I could have taken out, but there's a GCF of 2 here, so let's divide everything by 2. And now let's factor. So 10 times 12 is 120. I need two numbers that multiply to 120 and add to 19. 1 and 120, 2 and 60, 3 and 40, 4 and 30, 120 divided by 5. 5 and 24. But it would have to be a negative 5 and a positive 24, and that would be a negative 120. So I don't think so. How about 120 divided by 6? How about 120 divided by 7 doesn't go in? How about by 8? 8 and 15. How about 12? That's going to be 10. 9 doesn't go in. 10 and 12 and 11 doesn't go in. All right, maybe this doesn't factor. So then we'd have to use the quadratic formula. So let's try the quadratic formula. X equals negative 19 plus or minus the square root of 19 squared. Why did I write 12? 19 squared minus 4 times 10 times 12 over 2 times 10. Okay. So that was me checking factors of 120. So then 19 squared minus 4 times 10 times 12. Those were real. Oh, this should have been a 6. Look at that, guys. I divided everything by 2 except for that. Okay. This is why we don't do math at 8 o'clock in the morning. Let's try it again. Maybe it does factor. All right, I divided everything by 2, and that should have been a 6. So 6 times 10 is 60. Two numbers that multiply to 60 and add to 19. 2, 30, 3, 10, 4, and 15. So it does factor when you do it right. So these have a 2x in common. Plus 2. These have a 3 in common. 5x plus 2. 2x plus 3. So then this would be negative 2/5. And there was my 0 in between 0 and negative 1. And this would be negative 3/2. And there was my 0 in between negative 1 and negative 2. Okay. Oop, they wanted factors. All right. So as factors, this would be these 3 and these 2. So x minus 2 as a factor is x plus 2. X equals negative 2, excuse me, as a factor is x plus 2. And we have 2 of those. So that should be x plus 2 squared. And then this would give me x plus 1. And then we have these two factors, 5x plus 2 and 2x plus 3. Now, the only other thing that I need to do here is, remember how I divided out of 2? I GCF'd out of 2. So I have to put that back in front. Because really this all should have been like this. So this 2 that I GCF'd out on that step, it goes in front. Okay. Right. Now I'm still always going to factor first, even if they give me a 0, I'm going to factor. So let's see. Come on, calculator. So x to the 6th minus 7x to the 5th plus 40x to the fourth minus 186x to the third plus 377x to the second minus 275x plus 50. I'm just in the habit of double checking these because of how often I put them in wrong. 30x squared, 6x to the third, 377x squared, 275x, 50. Okay. All right. So it looks like here we have a 0 in between 0 and 1. We could zoom in on that section of the graph. Let's change our window. Oops. Let's change our window to like -1 to 5. And then again, -5 to 5. Okay, so we definitely have a 0 in between 0 and -1. We have 1 at 1, so let's see. Between 0 and 1. At 1. At 2. And then between, is this 1, 2, 3, between 4 and 5? Or is that between 3 and 4? Yeah, between 3 and 4. Okay. I'm going to just double check the table because I want to make sure that there are zeros at 1 and 2. And there are. Because sometimes your line looks like it goes through, but it's just really close. So if it looks like it goes through at a lattice point, then I'm always going to double check the table just to be 100% sure. So now I'm 100% sure about 1 and 2. And so this is a 6-degree polynomial, and I'm expecting 6 zeros. I have 1, 2, 3, 4. Bless you, baby. She just said bless you to herself. 1, 2, 3, 4. And then the one that they gave me 5i. But if you have 5i as a 0, then you also have -5i. The thing about imaginaries is that they always come in pairs. And so if you have one imaginary, you have its complex conjugate also. Okay, so them telling me 5i means that I also had -5i. Okay. So I'm going to do the same thing I did above, and I'm going to divide out the ones that I know. So I know 1, I know 2, I know 5i, I know -5i. So 1, -7, 40, -186, 377, -275, 50. Let's divide out the 1, multiply, add, multiply, add, multiply, 152. Multiply, literally just like too tired to minus 152, 225, multiply, that's going to be 50, it's going to be -50, multiply, add. Okay, so we divided out the 1, let's divide out the 2 next. Multiply, add, multiply, 34 minus 8, I know this. What? 34 times 8, 34 minus 8, 26. Multiply, that's going to be 52, add, that's going to be -100. Multiply, that's going to be -200. Add, that's going to be 25. Multiply, that's going to be 50. Add, that's going to be 0. Okay, now I'm going to divide out the 5i. Definitely going to want our calculators for this one. Because when I multiply 5i times 1, I get 5i. When I add -4 plus 5i, I get -4 plus 5i. Now I'm going to multiply 5i times -4 minus 5i. And I'm going to get 25 minus 20i negative 4 plus 5i. Negative 25. Right? Negative 4 plus 5i. Negative 25 plus 20i. And then I'm going to add 26 to that. And that's 1 minus 20i. Then I'm going to multiply that times 5i again. 100 plus 5i. And then I'm going to subtract 100, just 5i. Then I'm going to multiply 5i times 5i. Negative 25. That's why I said you're definitely going to want your calculator. So then let's do the negative 5i. Bring down the 1. 1 times a negative 5i is a negative 5i. Well, a negative 4 plus 5i minus 5i is just negative 4. And then a negative 4 times a negative 5i is a positive 20i. And then a 1 minus 20i plus 20i is just 1. And then 1 times a negative 5i is a negative 5i, and that's 0. Cool. And so then if this was t to the 6th, this is t to the 5th, 4th, 3rd squared. So this would be 1t squared minus 4t plus 1. So in factored form, we would say, I just realized all of these should have been w's. I hate it when Word does that. In factored form, this should be t minus 1, t minus 2, t minus 5i, t minus a negative 5i, so plus 5i. You okay?
No.
She's singing the song of her people. And then this doesn't factor. There are no two numbers that multiply to 1 and add to negative 4. So t squared minus 4t plus 1. Although it says as the product of linear factors. Interesting. I wonder if they want you to get the root for this one. You know what? I'm going to jump on more and I'm going to look at this problem because I want to make sure that I'm telling you the right thing, because I'm a little weirded out by the fact that this is the product of linear factors, because this is not linear. This is quadratic, but it doesn't factor. So we would have to use the quadratic formula and then just add or subtract that answer. So again, before we walk away, I want to make sure that I'm telling you the right thing and then I'm telling you how to put it in the right way. Here we go. Here's a polynomial functions. Almost. Here we go. Yeah. All right. So they want us to put this in the quadratic formula and get a radical. Okay, so let's do it. A is 1, B is negative 4, T is 1. So we would say that T equals a negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 over 2 times 1. That's going to be 16 minus 4 is 12. The square root of 12 is the same as the square root of 4 times the square root of 3. So that would be 2 rad 3. And then you can divide a 2 out. So then we would write this as, so if t equals 2 plus rad 3, right? And we want to make it equal 0, then we would subtract the 2 and subtract the rad 3. So that would be one of my factors. Minus 2 minus rad 3. And then if it was t equals 2 minus rad 3, then when I move this over, it would be t minus 2 plus rad 3. So that would be my last factor. T minus 2 plus rad 3.
Oh no!
What's wrong, baby?
Let go!
It's right there. Okay. But that's my final answer. G of t equals. Okay. G is a degree 5 polynomial that passes through the origin and has zeros at I, 8 minus I, and G of 5 equals 2600. Okay. So passes through the origin means that I know that I have the point 0, 0, which means that I know that x equals 0 is one of my zeros. I also know that x equals I, which means that I know that x equals negative I, because i's always come in pairs. I also know that x equals 8 minus I, which means that x also has to equal 8 plus I, because again, those always come in pairs. If you have one, you have the other, always. Okay, so this is 5 zeros, 1, 2, 3, 4, 5. Let's turn them into factors. So x equals 0 would just be an x. X equals I would be x minus I when I move the I over. X equals negative I would be x plus I when I move the I over. This would be x minus 8 plus I when I move both of these over. And this would be x minus 8 minus I when I move both of these over. Oh, they wanted t's. All right, I'll change them to t's on this step. So I also know that I have the point 5, 2600. So when I plug in a 5 for x, or t it should be, I should get 2600. And we did a problem just like this last time, where I said, okay, put an a in front, and that is the placeholder. I'm going to rewrite it. And that is the placeholder for my leading coefficient. So 2600 equals a times, and then everywhere I see an x, I'm going to change it to a 5, because you should get 2600 when your x's are 5s. 5 minus I, 5 plus I, 5 minus 8 plus I, 5 minus 8 minus I. Listen, there is 0 chance I'm doing that out long. 0.
Bye.
Who are you saying bye to? 5 minus I, 5 plus I, 5 minus 8 plus I, 5 minus 8 minus I. 1300. Okay, so when I plug in a 5, I get 1300. So then 2600 equals 1300A. So if we divide both sides by 1300, then A, which is my leading coefficient, is just 2. So then my final answer for this what did you do? Here you go. So then my final answer for this is G of t equals, they want it in factored form, right? assuming so. 2 times 2t t minus I, t plus I, t minus 8 minus I, minus 8 plus I, t minus 8 minus I. I'm like 98% sure that they don't want you to factor that, but I'm double checking on your homework right now so that I can be 100% sure. Too far. Not far enough. Yep, good. Factored form is fine. I was like, we're not multiplying all those together, are we?
9.
Okay. All right. So last but not least for this section, we have a polynomial of degree 6 with a leading coefficient of -1. So even degree, negative leading coefficient means that's what my end of behavior looks like. So on the right-hand side, as r goes to the right, k of r goes down. And as r goes to the left, k of r also goes down. Write the factors. So just like before, I know they gave me 4i, which means I also know -4i. I'm still going to graph this and see if there's anything that the graph can tell me. Negative x to the 6th minus 13x to the 5th minus 75x to the 4th minus 321x to the 3rd minus 1022 x to the 2nd, 1808x, 1248. I'm going to press zoom 6 to get my graph back to a standard window because I messed with the window before. And zoom 6 will always get me back to a standard viewing window. Thinking. Really? I didn't double check this one. Negative x to the 6th minus 13x to the 5th minus 1022. Ooh, look at that. To the 2nd minus 1808x. I checked the other ones and they were fine, and the first time I forgot to check, it was not fine. Okay, so it looks like I have a 0 at -2 and at -3. And then I have one in between -3 and -2, and one in between, what is this? 1, 2, 3, 4, -5 and -6. Let's double check those on the table. So yes, we definitely have zeros at -3 and -2. We also know we definitely have zeros at 4i and -4i because they told the 4i to us. And if they tell us one imaginary, then we know that its conjugate is also a 0. So I'm going to do my synthetic division again. -1, -13, -75, -321, 1022. Do it at the bottom. I thought I had enough room there. I do not. I do not. -1, -13, -75, 21, 1022, 1808, 1248. -3. Bring down the negative 1. That's going to be a positive 3. So add to negative 10, multiply positive 30, add negative 45, multiply 135, add, multiply, add, multiply, add, multiply. All right, let's do it again with negative 2. So that's 2, negative 8, 16, negative 2, 58 plus negative 186 times negative 2 minus 464 times negative 2. Phew. All right. Now let's do it with 4i. I might run out of room. Negative 1, so that's going to be a negative 4i. It's going to be negative 8 minus 4i. And then negative 8 4i times negative 8 minus 4i is 16 minus 32i. So that plus a negative 29. Negative 13 minus 32i times 4i. 128 minus 52i. So then just a minus 52i times 4i. 208. Cool. One more. Negative 4i. Negative 1. It's going to be a positive 4i. So that'll leave me with just a negative 8. Negative 8 times a negative 4i will be a positive 32i. And that'll leave me with a negative 13. Negative 13 times 4i would be a positive 52i. 0. Okay, that's all I can divide out. If this was t to the 6th, r to the 6th, this is r to the 5th, 4th, 3rd squared. So this is r squared minus 8r minus 13. Negative r squared. I'm going to GCF out a negative 1. There are no two numbers that multiply to 13 and add to 8. So then this would be r equals negative 8 plus or minus the square root of 8 squared minus 4 times 1 times 13. $64 minus 4 times 13, 12 over 2. We just said before the square root of 12 is 2 rad 3. So then negative 4 plus or minus 2 rad 3. Okay, so then my zeros are negative 3, negative 2, 4i, negative 4i, negative 4 plus 2 rad 3, negative 4 plus rad 3, negative 4 minus rad 3. And then as the product of linear factors, that would need the negative 1 in front. So this would be x plus t r, r plus 3, r plus 2, r minus 4i, r plus 4i. If we move these over, this would be a positive 4 minus the square root of 3 and a positive 4 minus the square root of 3 plus 4 minus the square root of 3. Ugh. The r-intercepts, the good news is we already found them. The r-intercepts are all of my real answers up here on zeros. So the r-intercepts would be negative 3, 0, negative 2, 0, negative 4 plus rad 3, 0, negative 4 minus rad 3, 0. We don't include the imaginaries because intercepts are a property of a graph, and a graph only needs real answers. Now I just noticed this says 3 decimal places, so let's figure out what those decimal places are. Negative 4 plus the square root of 3. So negative 2.28. And then negative 4 minus the square root of 3. Negative 5.732. Oof. And then the K of our intercept is negative 1248. All right, that was a lot. 3.6 is dense. The good news is a lot of it was repetitive. So if they give you a polynomial, even if they give you zeros, you should always graph it first. And then you're going to use synthetic division to divide out whatever they give you. That way, usually between the factors that they give you, or the zeros that they give you, and the zeros you can get from the graph, you can do enough to get down to a quadratic, and then you know what to do with quadratics. You're either going to factor them or use the quadratic formula. Okay?